Hey folks, so let me share my screen here and we'll get this thing rolling. Okay, so we're going to talk about energy today, and this is once again just a quick kind of an overview. You have the slides. I'm just going to kind of hit the important parts here, and then if you have any questions, text or email me. All right. So a couple of definitions for the class when we're talking about energy. What I want you to know is the capacity to do work, and work is a force over vertical distance. And that's important to remember because if you think about vertical distance, we're talking about gravity is always pulling us down and we're trying to move forward or some direction. So it's a vertical distance. We're keeping ourselves off the ground, basically, is how that works. So that's why it's a vertical distance. We can also express work in the unit of time, and that's called power. So it's the ability to use that force over vertical distance and how quickly you can do it. So that's really important when it comes to sports, right? Because we're trying to move as quickly as we can in a direction that we intend, to do whatever, hit a tennis ball or spike a volleyball or whatever it may be. So, and in this case, on the screen, trying to move a sumo wrestler. And if you look at the screen, obviously, the force that the sumo wrestler is applying to the ground is much greater than what the little kid can push or to use his force to move. If the little kid got a running start and added velocity to that or moved over a distance over time, he might even have a little greater impact, probably not much. But that is the definitions I want you to look at. So when we look at energy expenditure, it's how much energy is required then to do that work. And in nutrition, we call that calories. Now, calories with a capital C is the same as saying kilocalories or kilocalories. So just kind of keep that in mind. We use fairly small numbers when we talk about calories, like a soda you may be drinking is 140 calories per can. Well, that's a big C, so it's kilocalories. So you have to add a few zeros there if you were if you really want to be precise. In our world and in everybody else's world, when we're counting calories, we just call them calories and just assume that they're kilocalories. So what is a calorie? You can watch this video. It kind of describes it. Just make sure you download it. It works best. But basically, a calorie is a measure of heat. And you can see this. You can burn food and see the brightness of the flame. So if you burn something like a Cheerio, right, a little piece of oat, if you will, because it's mostly carbohydrate, it's going to burn bright. But if you burn something like a Frito or some sort of chip that has a lot of oil in it, it burns even brighter. And that's an indication of the amount of calories that it can give off. So the oat being 4 calories per gram because it's a carbohydrate, and the chip being mostly fat, so 9 calories, is going to burn brighter than the 4-calorie one. So it kind of gives you an idea then of how many calories might be in a food. Now, we don't go around and burn food all the time, right, to determine how many calories are in it. That's been done for us. We already know. When we look at the nutrition label or even on a supplement label, it'll tell us how many calories, and that's how they know. Somebody has done the work for us and has determined caloric content by how much heat it can give off. We also have to look at efficiency. So when we burn calories in our bodies, we usually describe it as a percentage of work. So 20% of energy is produced by the body is used to do some sort of movement. And then 80%, of course, these are rough numbers, 80% is then used to maintain homeostasis. And we can measure that as a loss of heat. We can also measure that by how much CO2 we breathe out too, because both heat is given off with muscle contraction and CO2 is given off within the Krebs cycle. So as we do more work or we contract more muscle, we produce more heat, or we create more CO2 as a byproduct of creating ATP, as we've discussed before. So that's how they measure that. That's how we get to those numbers. And you'll see here in a minute how we've actually put people in a box or had them breathe into a machine and determine how many calories or how much energy they're using to perform work, how many calories they're using to create ATP to create movement. So we're going to look at this. And so when we came up, not only do we have to look at how many calories we're burning, but we also have to know how many calories we're ingesting. So that's where we came up with the carbohydrate, fat, and proteins. So carbohydrates is really 4.2. We round that down to 4. Grams of fat are usually 1 gram of fat is 9.4. And we round that down to 9. So, one more point there, right? And we would be 10 calories. So fat really packs quite a powerful source of energy. Protein is also 4 calories, just like a carbohydrate. Once again, though, protein is the component of protein, amino acids, are really used to create more proteins. They really aren't recognized as our body to use as a fuel. So be really careful with that. Don't think that eating a steak before a race is going to provide you with 4 calories per gram. It might if your body recognized it, but oftentimes it sees those amino acids that you just ate, those proteins that you just ate, as a source to remodel or rebuild your body, not necessarily for a fuel. So keep that in mind. I described the flame. This video here will show you that flame. It's kind of a silly little thing they did on a news channel. And anyway, give it a view if you'd like to see it. It's not a silly. I want you to remember this guy. This is Wilbur Atwater. And in the late 1800s, early 1900s, he's the one that did the research on calories. So he's the one that determined when we break the bonds of carbohydrate, we get 4 calories per gram. When we break bonds, and it comes off as heat, in this case, of fat, we get 9, and then, of course, protein is 4. So Wilbur's the one that came up with those numbers. So we can thank Wilbur. Next time you have a question on the test on calories per gram of carbohydrates, think of old Wilbur Atwater. Handsome feller. Okay, so we're going to measure energy. This is energy expenditure. Sorry, it disappeared on the slide, or EE. And our energy expenditure ought to match our energy consumption. So what we expend during the day, we should also be at least matching. And if we match it, then of course we're not gaining any weight. If we're eating more or we're consuming more fuel or to create this work, then we're actually then we're going to gain weight. We're going to store it. And if we don't get enough, then we're going to lose weight because our body's just going to keep trying, right? And it's going to use other sources, fat primarily if we don't have carbohydrates on board. And in some cases, some rare occasions, we may even use protein that it gains from our muscle and other tissue. So we don't want to do that, right? We want to try to keep carbohydrates on board because that's our best source of fuel, especially and most importantly during competition. Unless, of course, your goal is to lose weight, right? And you're trying to burn calories from fat, then, of course, we can manipulate that so that we're burning more calories from fat and losing weight. So that's the idea. All biomechanical processes either give up heat, like with the myosin and actin contractions, that's going to give off heat, and the Krebs cycle produces CO2. So any biomechanical process that causes movement will either give up heat or CO2. And we can then measure energy expenditure by measuring the amount of heat or the amount of CO2, because we know that the harder we work, more heat, more CO2. So they've done a couple of different ways to do this. This is the most direct way. They put you in a box that's sealed. They pump in air so that you can breathe. They measure the air coming out. They run it through a cooler and then scrub it with some lye and lime. And then they can count how much CO2 came out. They can also put coils in the ceiling because heat rises, and they measure you in the box with the heat. Now they take into effect maybe the little bit of heat that the light bulb may be giving off, a little bit of friction that we may be radiating out because of the friction of the chain on the bike or what have you. And they calculate that out, but we look for the heat exchange. So the harder you ride, the more heat. The harder you ride, the more CO2. Well, that's just one way. Really inconvenient, right? Because how many of you guys are going to go sit in a box? And the box is flat, so What about hills? What about downhills? What about turning the bike? What about all of those and getting on and off of it, all of that stuff. So they have this thing called an indirect, and basically you wear a bag and you breathe into it. Now this is a little harder to exercise in, right? So this one isn't real functional for sports nutrition either, but it gives us a general idea of how many calories we'll burn at rest, gives us a really good idea of resting metabolic rate, and things like that. So there you go. Then we have a closed and open circuit one. And basically the closed circuit is you'll breathe in 100% oxygen and it should say air because no one breathes in 100% oxygen, right? Our atmosphere is about 20%. So if you breathe in the air, right, not through a mask is basically what that is. So they can manipulate the oxygen levels, which is kind of cool. So then they can manipulate like altitude and things like that. So they can really determine then whether or not you're in an aerobic state or an anaerobic state with or without oxygen. So that's kind of cool too. So once again, they use a soda lime and it absorbs the CO2, then they can measure it. They also have an open circuit where you breathe normal air, ambient air, and that's about 20% oxygen and a little CO2 and a bunch of nitrogen. So that's the other way they do it. And then that's more natural, right? Because that's what we do in a race. We're not wearing a mask full of, canned air. So this, you then have you on a treadmill and a bike and a stepper. Usually you're connected to something. So once again, this is a bit limiting because you have to be in a lab basically to do this. This can get a little bit more direct by using a chamber. Instead of just being on a bike, they can measure just about any activity you can possibly do within this chamber. Once again, it's sealed. They pump in the CO2 or air. They measure the CO2 coming out. There's heat coils in the ceiling, and they take into account the temperature of the TV and all the other things going on. And they can measure you for your activities of daily living. So how many calories you burn while you're reading or sleeping or typing on the computer. They've done it all, and we have data points for all of that stuff, which makes it really nice when we're trying to look up, how many calories am I burning by doing this homework or reading listening to this lecture. So it works that way as well. A Douglas bag is an inexpensive way to do a clinical test. This guy he's actually a indirect because the air is going into this and he's breathing it in. But when he breathes out, the valve checks and the air he breathes out goes into this bag over here. It's called a Douglas bag. This Douglas bag then fills up, of course, with his expelled air. And they measure the CO2. They hook this bag up to a machine and measure his CO2. Pretty popular with researchers because it's inexpensive, and you can either take the university may just have one computer that does a diagnostic, and they can take this bag to that computer. They don't have to actually take the subject to it. If you have a more money, you can get a breath by breath system. Basically, you do the same thing. You breathe in regular air, and this one they can actually hook up a direct line so that you're breathing in whatever they want to give you as well. So they can do it either way. And instead of breathing into a Douglas bag, it goes directly into a computer to analyze the CO2. I've done this actually in college on a treadmill, and they measured my VO2 max in preparation for another study that they were doing. And I got like $15 for it. So that's cool, I guess. Back in the day, that was a lot of money. So you can, in your big labs, like at AASU, they do a lot of exercise phys work. They'll do this stuff, and they'll put a notice out for people to be part of the experiment. And sometimes they pay you. The trick is, guys, the more expensive it is, the more they pay. So, I mean, the more it hurts, the more uncomfortable it is, the more they pay. So, what's cool about this one is they can do it in real time, right? They don't have to wait for the Douglas bag to be shipped out, and you can get numbers in real time. So, if you like what you see at a certain rate, a certain miles per hour on a certain elevation, you can then crank it up or slow it down and then see what it does. So that's kind of cool. There's some more evasive ways they can eject you with radioisotopes or isotopes, and it binds with CO2, and they can then test it. This doesn't last long. It's good for a little bit, but who wants to get shot up with heavy water? So they don't use that one very often. They can use the same thing like heavy water, and they can it's injected into your body, and then it's bound to your CO2 when you breathe it out. This one up here is usually through they through urine and things like that. So this one you can breathe. It's called labeled bicarbonate. And then, of course, everybody I think is familiar with a heart monitor. This is really the one that we use a lot in our daily lives, not necessarily in a lab, right? You put on a heart monitor, and most of the time now, right, people have smartwatches that do the pretty much the same thing. They're fairly accurate. They're more accurate than they've ever been. This used to be what you had to do even 10 years ago to get an accurate reading. And of course, there's these accelerometers, and you've got this in your smartwatch as well. They used to be able to wear these and clip them under your belt and then walk, and it would have a little bead in it and swing back and forth and count how many times you walk. Now we're a little more complicated. We can put them on our wrist and use our smartphones to tell us, how far we've walked, and all that is calculated, of course. And it's not necessarily looking at CO2 or even heat. At this point, these watches are just looking for movement and then comparing how much we've moved to the data points that have already been collected through tons of research for, dozens of years. And so it just compares the results. So Apple has gotten really good at this. They can even determine what kind of stroke you're using in the pool. So if you're put it on swim mode, you swim, and then you can look back and it'll say, if you do 400 yards, it'll say so many yards of freestyle, so many yards of breaststroke, and a mixed stroke of so many yards. So they can determine how, what stroke you're using. So they're really getting good, at this. So it's kind of cool. And then, of course, the old school, just activity record, and then you just look it up. I used to have to look it up in a book. Matter of fact, my book's on my shelf over there. Right over there. It's still there. Maybe I'll grab it. So before computers, they have a thing called for running. They had a little book out for running, and that's it. That's what I had to use at one time to determine. This is back in the 90s. I had to use this thing to determine energy expenditure and then timetables for running. So basically, you would look this stuff up, and it had a bunch of statistics in it and scales. And then, of course, it's filled in between on how to use it. I mean, it was ridiculous, but this is what we had to use. So I tabbed it so I could get to it really quick. Anyway, you're lucky. It's pretty much turn on your computer, point and click, and now you can get the same thing. So lucky you guys. Basically, what that determined with all of that study of people sitting in boxes and measuring their CO2 and measuring their heat is this thing called resting metabolic rate. Now, resting metabolic rate is what your body has to use as fuel to maintain you in the state that you are right now. So in your physical fitness condition, with your lean body mass or your fat mass or your bone mass, all of that added together. And it accounts for about 60 to 70% of our daily energy expenditure, or our metabolic rate. Your RMR is influenced by your age, gender, and body composition. And now body composition is really important here. So the more muscle mass you have, and this is important, it's on your test, the more muscle mass you have, right, the more energy you need is required to support that muscle mass. Okay, so if you are trying to lose fat weight, you're trying to, thin down, you should lift weights, because at rest, your body's going to require more energy to maintain that muscle mass that you've just put on. So you'll burn more calories at rest, which is kind of a bonus, right? So make sure you remember that. Resting metabolic rate is influenced by all of those things, but it's really influenced, right, by body composition. So the more muscle mass you have, the more energy you expend at rest. Now, genetic factors. Some of us just have a high metabolism. Age, we can't control that. This really should say biological sex. So, right, gender really has become like a social thing. So it really is biological sex. If you're a male, you tend to have more body muscle mass than female, and so you burn more calories at rest. So that's where that influence comes up. Your resting metabolic rate slows down with age, so which makes sense, because so does your max heart rate. So if you were determined to going to determine your max heart rate. It's 220 minus your age. So if you're 20 years old, your max heart rate's 200. 220 minus 50 obviously is, well, help me with the math. So it's much, it's much slower. So obviously your age is going to influence your RMR. It decreases the older you get because your heart rate can't get that high. So your intensity doesn't go up as much. So there you go. Once again, RMR is higher in males because of muscle mass. Now, RMR, right, resting metabolic rate, maintaining who you are, and something called DIT, or your diet-induced thermogenesis, makes up what we call your BMR. Now, your BMR is your basal metabolic rate. You combine your RMR and your DIT, and you get basal metabolic rate. Okay, and basically that's just how much energy your smooth muscle is requiring to maintain the peristalsis contraction. And this is about 10% of your daily expenditure. Okay, so add that 10% then to your RMR, right? So now you're at somewhere between 70 and 80%. That makes sense to that last slide. So diet into your diet, or what you're digesting and how you're doing that, it influences your basal metabolic rate. Once you've determined your basal metabolic rate, you kind of know how many calories you need to maintain you, okay? To maintain you and to digest the food you eat. And then what we can do, and we can really influence how many calories we're expending, is this thermal effect of exercise. Now, we can do this voluntarily, and that's what you choose to do, and we do it involuntarily, and that's just the little stuff we do. It's the fidgeting, the moving, the shivering. That's the thermal effect of exercise. And the reason it fits into this exercise bit, because we're just talking about muscle contraction. So if you're in cold weather, you're going to burn more calories because your muscles are going to be moving more to create heat to warm you up. Okay, so that's important to remember. So those are the three factors that contribute to your caloric burn: resting metabolic rate, and your DIT, and your thermal effect of exercise. Now, oftentimes in the lectures and in class, you'll see me just say BMR. Well, BMR, that basal metabolic rate, is your RMR and your DIT. So don't forget that. Try to say that over and over again. Rewind this thing. Rewind. No one rewinds anymore. Play it back. Say energy balance. This is you're going to do those assignments. So you're going to see if you're in debt or in excess. And if your intake equals your energy expenditure, then you're not going to gain or lose weight. Obviously, if your intake is greater, if you're taking in more calories than you're using, you're going to gain weight. And if your intake is less, then of course you're going to lose weight. So, all right. So here's the terms you need to remember. Text, email me if you have any questions, and you're doing great. So keep up the hard work.